Hi, and welcome to this presentation as part of iolite's Python for LA-ICP-MS course. In today's presentation, we'll be talking about data reduction schemes. To give you an overview of what we'll be looking at, we'll start off with DRS modules, talking about DRS modules in general. Then we'll look at the settings widget, which is how the user sets values to be used in the DRS. And then we'll be looking at some of the calculations that you might want to include in your DRS. But before we get started, I just thought I'd mention some general principles about writing DRSs and how iolite and DRSs are combined. In general, we try to create a new channel for each step of the DRS. This is so that the user can check what the effect of each step was. In theory, this prevents iolite from becoming a black box, so that the user could go and check, for example, what effect the first baseline subtraction step had, because they could look at their raw data and they could look at the result of the baseline subtraction step, and they could see if something was going wrong. It's like, well, do these data make sense? Yes, they do. Then the problem must be somewhere else. So that's the idea behind it, and it's good practice that for each step you create a new channel and name it something so that the user can tell what step this represents. You're probably already aware that channels are arranged into input, intermediate, and output channels. This is because input channels are generally the raw data that's come from the mass spectrometer. And iolite doesn't change that at all. This is good practice so that the user could check the input data in their experiment against their raw files and make sure that the input process has been complete. Also, it means that you can run the DRS as many times as you like because we're not changing the input channels in the DRS. We're just acting on those to create intermediate and output channels. The intermediate and output channels were, in the past, the output channels were generally channels that you'd like to report a result for. So if you're calculating isotope ratios, you would put your final ratios in the output category, and iolite would report, when you exported your results, some statistics for those channels. Of course, in iolite 4, you can report values for input, intermediate, or output channels, but it still holds as good practice to separate those channels that are used to work towards your final channels as intermediate and keeping your final results in your output channels. It's also important to recognize that the DRS just calculates channels. It doesn't actually calculate the statistics for each selection. That's done by iolite's results manager, and that's normally done after the DRS runs. The DRS calculates the channels, and for every selection, the results manager will calculate some statistics for every channel for that selection. Now, this creates a one-to-one relationship between the selection and each of the channels, and this happens for all of the selections, but it is a one-to-one relationship. For each result, it is related to one selection and one channel. However, there will be times where you'll want to calculate a result that's based on a selection, but it's based on more than one channel. And we call these associated results because they are based on more than one channel. A really sort of obvious example for this is a correlation between two channels. So it's still linked to that selection because it's the correlation only during that selection, but it's based on more than one channel. It's based on two channels and the correlation between the two. And because of this, these associated results are treated slightly differently than normal results in iolite. And we'll show how to set those up towards the end of this presentation. But they can be set up in your DRS. And as I said, the most common example for this is an error correlation. Sorry, a correlation between two channels. So, how to create a new custom DRS? Well, you can go to the DRS view, and in the top left corner up here, there is this new button that you can click, and it will create a new DRS file for you. It'll prompt you for some information such as a name for it and a description. You should put some values in there. And then when you open that, it will be the basic DRS template for creating a DRS. And it'll put it in the data reduction schemes folder that is set in iolite's preferences in the paths section. So what is a DRS module? Well, the module itself is just like the import modules or the QA/QC modules that we've seen in the past, in that it starts with some metadata. But in this case, the type has this value of DRS. This tells iolite to treat this script as a DRS. So it will appear in the list of DRSs in the DRS view, and it will be expected to have certain functions. The other metadata fields, the name, the authors, the descriptions, etc., they're the same as the other modules, and you can put whatever values you like in there. Of course, we recommend that you put in accurate descriptions so that the user can tell what this DRS does, but you can put anything you like in there. There are two required functions in a DRS module. There's the run DRS function and there's the settings widget function. And as we'll cover those in more detail later on. Just like in the other modules, you can access iolite's data manager via the data keyword. You can access iolite's logging module and messages view via the iolog keyword. And in the case of a DRS, there's also this DRS keyword that allows you to access certain functions that are particular to data reduction schemes. So let's have a look at the DRS object itself. If you type in DRS dot, you will have these functions available. The first is settings. This retrieves the dictionary of settings that the DRS uses to store all of the settings. So all of the settings, such as the primary reference material, the index channel, those types of things, are stored as a dictionary in the DRS. And by calling drs.settings, you can retrieve that dictionary and get those values. You can also set default settings using this function. And remember, because it's stored in a dictionary, each value in the dictionary has a key. That's its name, so we have to give it a name and the value. You can also set the settings via set setting, and name and value are very similar to the default setting. There's also this set settings widget, which we'll come back to when we talk about the settings widget. And there's this baseline subtract function. We'll come back to that when we talk about baseline subtractions. There's also an update splines function, which will recalculate the splines using what has been calculated in the DRS up to this point. This makes sure that when your DRS continues, it's using the most recently calculated values. There's also some functions to create masks, and this is the most basic one, which will mask out all of your background regions. It'll mask out every time the laser log says that the laser was off. And this is really useful, as hopefully you're aware that masking your results allows you to, it reduces the range in ratios that you see because you get a lot of noise in your baselines. There are a couple of other options for this create mask. There's a couple of other functions, and I'll refer you to the API on the website for those, but they're very simple. They just take a couple of parameters and you can create masks from those. There are also some signals, just like in the previous modules that we've looked at. The first is the message signal, and this is the message that's shown in the progress indicator while the DRS is running. So this alerts the user as to what's happening at this step of the DRS. And there's also the progress function, the progress signal as well, which takes an integer between 0 and 100, and that's the percentage that is completed in the DRS, and you can use those to keep the user updated on how far through the DRS that you're up to. There's also this DRS.finished function that lets iolite know when the DRS has finished, so it will recalculate all of the results and it will update the user interface. So it's really important that you call that anytime the DRS finishes. And I say anytime that the DRS finishes because you might exit early because the user hasn't provided some value that you need. For example, they haven't selected their reference material selections yet, and you'll want to finish the DRS at that point, and you'll need to let iolite know that the DRS is finished by calling this DRS.finished. So you call it any time that the DRS stops or at the end of the DRS. So now let's look at the two functions that are required by the DRS module. The first is the runDRS function. And this is the function that is called when the user actually clicks that crunch data button. This is the one that actually creates all the channels. But there is also this settings widget function that's required that creates and populates the widget the user sees and uses to interact with the values to be used in the DRS. So this is where they set things like the index channel or the primary reference material. And that's all done via the settings widget. So by the settings widget, I mean that in the DRS view, you have on your left-hand side your list of DRSs, and when the user clicks on one of those DRSs, they're presented with the settings widget for that DRS. And that's what shows in this right-hand side or right part of this window, which is shown with this orange rectangle. That's what the settings widget is. And as you'll know from using iolite in the past, that this is where you set all your settings for the DRS. Now, we normally set the widgets and the controls in this widget up. We lay them out in what's called a form layout. And a form layout is just a neat way of arranging the controls so that each one has a label and that they are nice and neatly laid out one after another in this widget. If we don't have a layout, they can overlap with one another, they can be hidden, they can be off screen, that type of thing. So we make sure that we use a layout to put our controls into. And by control here, I mean things like a checkbox, such as a checkbox that the user can click whether or not they want to, say, mask their results or not. They can check it or uncheck it. A combo box, which is like a drop-down menu or a pop-up menu, as sometimes called as well. It's a way of selecting one of several values. We also have these things called line edits, which is basically just a field where the user can type in data, type in a value. So it could be a string or it could be some value it's like a threshold value or a ratio value to use within the DRS. And that's all done via a line edit. So for each control, we have a label and a control, the control widget itself. So let's look at a very basic example of what might be in a settings widget function. So it starts off with this import from iolite, this cute GUI package. This allows us to create the widgets that will be shown in the widget. So this will allow us to create combo boxes and form layouts and those sorts of things. So this is all the graphical user interface GUI components that we want to have. I've left a few dots there to say that there would normally be some other code before we get to this point. And then we get to the actual settings widget function, this part here. And we'd start off by creating a widget by calling cuteGUI.QWidget. This one doesn't have a parent in this particular case, so it has nothing in the brackets here. And that is our widget that will be shown. This is our main widget that will be shown to the user. And then we want to create a form layout. This is the layout that will arrange our controls nice and neatly. We do that by calling cuteGUI.QFormLayout. And then we tell iolite to use that layout in the widget by calling this widget.setLayout, and we pass this form layout that we've just created here, and then it will start using this form layout. So now we can start creating controls that will be shown for the user. And I've just put in one control here because it follows it follows this repeating pattern. You start off by creating the control that you want. So in this case, we're creating a combo box so the user can select which index channel to use. We do that by giving it some sort of variable name, in this case index combo box, and we create a combo box here by calling QtGUI.QComboBox, and it takes this widget, which is this widget that we created up here, as the parameter in this, so that the parent of this combo box is this widget. Then we would add items to the combo box so that the user has a series of items, a list of items that they can choose from. In this case, we're going to give them a list of all the input channels so they can choose one of those as their index channel. And we just do that by using this .addItems function, and we're going to pass it a list of time series names by calling the data manager and this function here. Then we'll set the combo box to have a default value. In this case here, we're getting the default value from the settings dictionary. In this case, I would have already set that. I haven't put that in here, but I would have already set that to have some default index channel, and that would then set the combo box to have that by default. Then what we're doing here is we're setting it up so that we're connecting this signal that when the combo box is activated, so the user has clicked on it to interact with it, anything that the user does will be recorded by connecting this signal with this lambda function. And all this lambda function does is it takes the text that's in the combo box at the moment, that's currently selected in the combo box, and it passes that to this drs.setSettings function, and we're telling it to update the setting called index channel with the text. So it's just updating our settings dictionary, and in particular this index channel value here. And then the final thing we do is we add the control to the form layout by saying form layout.addRow, the label that we want to put next to this control, and the actual control itself. And we'd keep doing that for as many controls as we want to add. If you want to see some examples of this, please feel free to see the example DRSs on iolite's GitHub page. And the final thing we do is we call the drs.setSettings widget and pass it this widget that we've created that has all our controls that we've added in here, and we pass that to it, and that will then tell iolite which widget to use. So these are some of the signals that you'll want to know about for the different control types. I generally look these up each time, but just to save you from doing that, here's some of the most common ones. So if you're using a combo box, as I mentioned, this is a drop-down menu, you'll want to use this text-activated signal and just connect it up to drs.setSetting and whatever setting you're trying to update. If you're using a line edit, as I mentioned, this is where the user can enter values. You'll want to use this text changed signal. So whenever the text is changed by the user, you'll want to connect that up to this function here, which takes the text and it updates the DRS settings. You give it the label of the setting you want to update. And if you want that setting to be a number, you would wrap it in this float function. If it's just text, you can leave that off. In this case, we would be setting a mask threshold, a value below which we will mask our results. So that's actually a number, so we're wrapping it in this float function here. And if you're using a checkbox, you just want to use this toggled signal, and whenever the user clicks on the checkbox, that will run this lambda function here that sets this particular setting. In this case, it's called mask, and in this case, it's changing this text to a boolean, whether or not it's true or false. As I mentioned, we create settings in our DRS by using this drs.setSettings. So we would create a setting via this function where we say the name of the value that we want to set, and then the actual value that we want to set. So in this case, we're actually just passing it a string variable. We could pass it a literal string. In this case, we're passing a Boolean, and again, here's another string variable. And as I mentioned, the last thing you should do is always to call this drs.setSettingsWidget and passing the widget that you've created at the end of this settings widget function. So that's how you create a settings widget to present to the user the controls that they can enter values into to be used when the DRS runs. Now let's look at the actual function that runs when the user clicks the crunch data button. Generally, you'll want to start by, after the function is defined, by printing out a message that just tells the user which DRS is running and setting the progress to 0. So this will just update that progress indicator in the bottom right. The next thing that I tend to do is I just extract the settings dictionary to a variable called settings. It's exactly the same, it just cuts off this DRS dot part. You could just use this throughout. It's only going to save 4 characters, but I find that conceptually works better for me. And then I recommend printing out the settings every time the DRS starts, so you can see what values have been set when the DRS starts running. This can be really useful for problem solving and debugging. Now note that this is going to be printed out to the Python console. The user won't see it unless they have the Python console open. So now let's look at some example calculations. This is the real crux of the DRS and how to create channels of your own and how to perform some common calculations that you would want to do in a DRS. So let's look first at getting channel data. So you would have seen in the past the simple mode of getting channel data from the data manager by calling data.timeSeries and then the name of the time series that you want. However, you don't always know the name of the time series that you want. For example, on a multi-collector, sometimes the channels are listed by M followed by the mass. Now, if it was strontium-88 as our example, and most of our examples today will be looking at strontium because I've been working on that recently, but quite often it's listed by the mass spectrometer as strontium-88. But if it's a multi-collector, it might be listed as M for mass, M88. In some mass spectrometers, it's actually M87.998 or mass 88.001 or something like that, where it's actually recording the exact mass that was the center of the peak that was being used. I just mentioned that because we don't always know the name of the channel that we want to work on. So we've given you some other ways to get the channel data. One way is by using the channel properties. And we get that by calling data.timeSeriesList. And in this, we list what type of channel that we're looking at. So if it's an intermediate channel or an input channel. And then we pass a dictionary of channel properties that we want to select by. So quite often there'll be a mass property for each channel, and we can use that to select our channel. Note that this returns a list, so we'd actually call 0 on this to get the first entry in this list to come back as our strontium-88 channel. However, as I said, sometimes the mass isn't listed as this nice whole number, and if it was 87.998, this wouldn't actually return the channel that we want. It may not return anything. So we also give this option of getting the channel by mass with a certain tolerance. And we do that by using this data.timeSeriesByMass, and then we tell it what type of channel we want, and then the mass of the channel and the tolerance that we will allow. So you shouldn't make this value too large so that it accidentally selects the wrong channel, but you also don't want to make it too small so that it doesn't select the channel that you're after. Now, in all of these cases, up to this point, and in this one up to this point, we're returning a time series object, a time series data object. And we can get the NumPy array of data values associated with that channel by calling .data on these, which has already been done here. Or we can get the time stamps, the time array for that channel by calling .time. So that's how we would access input channels, but how do we create our new channels, new channels? The way that we do that is we call iolite's data manager and we call this create time series function. And before we call this function, we need to create an array of values for our channel. And I'll show an example of that in just a sec. But this create time series function allows us to give the channel a name, a type, i.e. whether it's an intermediate or output channel, the time array for that channel, and the data array, the array of data values for that channel. So let's just look at a very simple example. Let's say we wanted to calculate the strontium-89 channel, and that was based on strontium-88, some relationship between the two. These are just made up numbers for this example. So what we do is we use this existing channel, strontium-88 underscore CPS, as a template for our new channel. So we would get our strontium-88 channel, the data array for that channel, then we'd multiply the array by some number that would give us our new array of values for our new channel. And then we would call this data create time series function. We'd give it the name of our new channel, what type it is, and we'd give it the time array that it's based on, and the strontium, and the new array of values that we've calculated here. Here's another example where we're creating a new ratio channel. This is a channel based on two existing channels. To do that, we'd get our two existing channels. In this case, we're looking at strontium-87 and strontium-86. And once we've got the arrays of data values for those by calling data, we just ratio one to the other, and that would create a new ratio channel. And then we would pass that in create time series as our data array. Now you'll notice here that I've given it a name, and you may want to give it a more expressive name because in a DRS you might have different versions of each ratio. So it might be a raw, it might be downhole corrected, or it might be final. So you might want to give it a more expressive name. We give it what type it is, and then we give it a time array and then the array of channel values. Now you'll notice here that I've actually passed it index time rather than the time array of one of these channels here. And the reason for that is because not all channels necessarily have the same number of data points. So why is that? Well, you remember that, or you may be aware that iolite will allow situations like this, where we have one file that has 4 masses in it, and then in the next file, one of those masses has been dropped out or omitted, and then in the following file, it's back in again. Now, the reason why iolite allows that and doesn't call that an error is because this channel that's been omitted might just be monitoring some interference or some unimportant value, and as long as it's not needed to calculate all of the rest of the results, it can be omitted and iolite won't report that as an error. But it does have the effect that the lithium-7 channel will have fewer points in it than the other 3 channels because it'll be missing all the points that are in this second file. So we can't assume that all input channels have the same number of points. So we normally get around that by defining index time, this index time array. And that's normally the time array of the index channel, and we interpolate all channels, intermediate and output channels, onto that array. Normally the interpolation step is done automatically, but if you wanted to do it manually, it would look like this. You would get your index channel, and you would take your input channel, and you would interpolate by using numpy.interp, and you'd be interpolating it onto the index channel's time array, and you would pass the input channel's time array and its data array, and that would give you your interpolated data. Now, I only mention that for completeness because normally you wouldn't do this, you wouldn't have to do this, because iolite has a built-in function that does this for you. So let's look at that now. This is the baseline subtraction function. And what it does is it takes your input channels and it interpolates all of them onto onto index time, and it also subtracts the baseline all in one step. And so that will give you your intermediate channels and your baseline subtracted channels all done in one step, and then you don't have to interpolate and worry about interpolation. After this step, all the channels that come out of this process will all have the same number of points interpolated onto index time. Now it takes the baseline group, the group that you want to use for your baselines. It's the actual group itself, not the name of the group. It takes a list of channels that you want to be baseline subtracted. Normally this is just your list of input channels. It will take a mask array. Normally before you run this step you will have created your mask, and then it just takes a couple of integers that will be shown to the user as so if this baseline step takes between 15 to 25% of your DRS, then you'd put in 15 here and 25 here, and that will just update the progress indicator between those values as it does the baseline subtraction. As I mentioned, you want to set up your mask array before that, and you can do that by either create mask from cutoff, where there's a channel and a cutoff value and some trim values, or you can do it from mask from laser log. You could also potentially just pass it a numpy array of all ones at this point here as well, so that you don't have to run one of these. Now let's look at interference corrections, because that's another very common task for DRS to calculate. There's a couple of ways of doing this, and to start off with, we'll look at the simple version that doesn't include any correction for mass bias. Now the way that we do this is we would get our channel that has some interference on it. In this case we're taking strontium-87 as our channel. It in reality may be some combination of strontium-87 and rubidium-87, and we want to subtract this rubidium-87 off so that we just have strontium-87. So we would also call our rubidium-85, which is a different isotope that doesn't have any strontium on it. We would get that channel as well. Then we would multiply the strontium-85 by the rubidium-87-85 ratio to work out what our rubidium-87 is based on this rubidium-85 channel, and then we subtract that rubidium-87 value from our 87, our combined channel, and this will give us our corrected 87 channel channel results. And then we create a new channel from that array. So we would call it something like strontium-87_C for corrected, and we would pass it the index channel time array and this new array that we've calculated here. So that's all it takes to do a very simple interference correction. But now let's have a look at some of the more complicated mass fractionation equations that we can use to do even more accurate interference corrections if you're working on things like isotope ratios. So all of this mass fractionation equations that I'll be showing are based on the Russell et al. Equation, which has this citation down here. But it's based on this pretty simple equation that says that the true ratio is a product of the observed ratio multiplied by the atomic mass ratio of the two masses involved to the power of some fractionation factor. And we can work out what the true ratio is by putting in our our observed ratio, so taking the array of 87 to 85 values, for example, and multiplying them by the atomic masses and to our fractionation factor here, this F value. Similarly, we can work out what this F value is beforehand by taking some observations and knowing what the true value is. When I say true here, I basically mean the accepted value of the ratio, and dividing that by the natural log of the atomic masses. Now, in a DRS, this would actually look like this, and we're going to be using strontium-88 to strontium-86 as our example ratio. So in this case, we would have our true value here, which is this value here, and that would be the 88 to 86 ratio value that comes from our reference material. And so we'd get that from our reference material file, and we'd use that in this calculation here. And the reason why this is a variable and it's not hard-coded is because we may have different 88 to 86 values in our either in our reference material file or that the user has entered a different value here. So that's the only reason that that is a variable. Whereas over here, the atomic masses are not variables because they're always the same. Then we would have our observed ratio here. So these are the arrays of strontium-88 and strontium-86. That would make up this observed value here, and that's put into the numpy.log function, and that will create this top line here. In the bottom line, we're using numpy.log, and we're doing that on the atomic masses, and that would actually work out our strontium fractionation factor. So this would be the F that we could then use in that previous equation to work out the true value of our ratio. Similarly, we can use this fractionation value that's calculated based on our reference materials and known ratios to calculate the interference of one isotope on another, taking into account mass fractionation. So again, looking at that equation, we can rearrange it so that we're looking at the observed ratio instead of the true ratio or the fractionation factor. And then if we were, for example, looking at trying to work out the 87 rubidium based on our 85, we would rearrange the equation to look like this. And then we just multiply both sides by rubidium 85, the rubidium 85 values, to work out our rubidium 87, observed rubidium 87 values. Now, why is it important that we use the observed value rather than the true value? Well, when you're doing isotope ratios at very high precision, this value is going to be different. It's going to be fractionated from the true value. So we want to make sure that we take that into account. There'll be a little bit more 87 observed than what we'd expect based on the true value. So what would that look like? So what would interference correction with mass bias look like? Well, again, we would get our interfered channel. We would get our monitoring channel. Again, this is going to be rubidium 85. And then we would put in our true rubidium 87, rubidium 85 ratio, and we divide by, we divide that by the atomic mass ratio to the power of our rubidium fractionation. So we worked out our rubidium fractionation factor earlier on, and then we would use that to calculate our observed rubidium 87. And then just like in before, we'd subtract this observed rubidium 87 signal from our total 87 signal to calculate our strontium 87 corrected value. And again, we'd create a new channel from that. Now, in those discussion of mass bias corrections, I mentioned that sometimes you might want to get values from the reference material, whether this be the accepted value for a particular ratio, or if it's concentration or some other property of the reference material. And we can do that by calling this data reference material data function. And it takes the name of a reference material and it returns a dictionary of result objects. So for example, if you wanted to get the 87 strontium to 86 strontium ratio from your reference material, you would pass the reference material name, which returns the dictionary. Then we would tell it the name of the key that we want. That would return the result for that. And then to get the actual value, we'd call the value function. So these parts here are required to actually get the value. If we had instead .uncertainty after that, that would return the uncertainty of this result here. Similarly, we can get spline data for any of our channels. Now this is really important, especially for things like fractionation factors. We don't want to know what the fractionation factor is for our samples because we don't know what the true ratio value is for those. We would want to use the spline of that channel, for example our, say, rubidium fractionation channel. We want to use the spline of that, but only looking at our reference materials where we know that those values are correct. And we do that by getting the spline. Before we get the spline data, we probably want to call data.update results. And this will recalculate all our results, including recalculating our splines. And then we would call data.spline. We give it the reference material name and the channel that we want the spline for. And this will return a time series data object, so the ones that we can call .data or .time on, for our spline. And that will already be interpolated onto index time as well. So for example, if we wanted to get the spline of our final corrected 87-86 ratio numbers, just for our reference material, we would call data spline, our reference material name, the name of the channel, and then we'd call .data, and then we'd have a numpy array of the spline values, which we can then use to normalize our results. And to do that, we would call this channel, which as I mentioned was the final corrected values, and we'd multiply them by the true value, the accepted value for our standard, and divide it by the observed value, which is the standard spline. And that would give us our standard corrected strontium 87-86 array. And we could create a new channel based on that, just like we've done in the past. So that's how you would normalize to reference material values, by getting the accepted value, by getting the spline, and multiplying by the accepted value and dividing by the spline. Another thing that's quite often done in DRS calculations, or could be done perhaps more, and is only really relevant for spot analyses, is correcting for downhole fractionation. Now, there's quite a few things that go into this downhole fractionation correction, so let's step through it in order of what we would need. So we need some estimate of the pit depth, and we call this in iolite beam seconds. We don't actually measure the depth, we use the amount of time that the laser has been on for as a proxy for pit depth. So we call it beam seconds, and that is our estimate of pit depth. And we can use this drs.create beam seconds from laser log function to create a channel called beam seconds. So it will automatically create a channel called beam seconds that every time the laser switches on, as recorded by the laser log file, and it starts increasing from 0, going up one for every second until the laser switches off again. And that will be our proxy of pit depth for all of our samples. Then we can get that array to use in our DRS by referring to that time series. Now, to get the downhole data, the average downhole data for a selection group, we can use this compile downhole function that's provided from the data manager. And what this does is you tell it what group you want the data for, what channel you want the data for, and you can also pass it this optional beam seconds max parameter, which will when the data go above that value, it won't won't include those data anymore. And what this does is that it will take all the selections within that group, and it will line up all their beam seconds equals 0 start points, and it will average for each measurement the downhole value for that channel. And it actually returns a tuple. In position 0 is the time array, which is basically beam seconds, and in position 1 is the mean downhole data. So it does it all for you, and you can use that so that's your observed downhole model, so your observed downhole fractionation. And then you can use that to calculate your model and correct for it. Before you do that though, you probably want to get rid of your blank values, any blank values that might be in that data. Blank values might be because a particular selection didn't have any data in that particular value, and those blank values will upset any fitting that you try to do to those data. So we can get rid of those by using numpy's isNan function, and we just pass it if we returned these tuples as a variable called DHF for our downhole fractionation data, and in position 1 we have the mean downhole data. This will create an array that equals 1 or is true wherever there is a nan, and then we can use this expression here to exclude any values in the time array, which is position 0, where there's a nan, by using this tilde DHF nans, and we can do the same thing for our downhole values as well. So that will get rid of the nans by using these 3 lines here, and then we're ready to fit some model to that so that we can correct for it. First thing that we want to do is import from SciPy their curve fit function, and this will automatically try to fit a line to it, and it will give us some estimate of the quality of that fit as well if we want to use that. Then we'll want to define a function to model the data. So if, for example, we thought our downhole fit was a linear function, we'd create a function that takes the downhole time, so the beam seconds time, and has 2 parameters to it, an intercept and a gradient. And it will take those values and multiply them, multiply by the gradient and add the intercept. And all this is doing is setting it up so that we can pass that into SciPy's curve fit function. So what SciPy's curve fit function does is it takes a function like the one we've defined here, and it takes the x data and the y data to feed into that function, and it will return the parameters of that function. You can set a fit tolerance to that. By default, it's 1e to the minus 5. You can change that if it's not completing or if you're not getting results. But basically, it will pass back some parameters, which will basically be a and b, and it also pass back the covariance matrix for that as well. Normally we don't use this covariance matrix, but if you're interested in the statistics of it, you can. Most often we'll just use the parameters. And in this case, the slope, which would be b, would be parameters at position 1, and the intercept would be parameters at position 0. Now we can actually use this model, which we've calculated based on our downhole, our beam seconds and our average downhole values, and we can correct for them here. So this is an example using lead-206 to uranium-238, and you just plug in the parameters here, multiply them by beam seconds, so it'll actually flatten the data back to being at the start of the selection. So that's basically just a formula that you can plug in your different ratios, your raw ratio data and your downhole corrected data into, and you can calculate your parameters for each of your ratios. Finally, we'll just look at propagating errors. We'll just touch on it very quickly. There is this data.propagateErrors function. It takes the selection groups that you want to apply the excess uncertainty to. So this will normally be all the selection groups apart from your baselines and your the primary reference material that you're using to calculate it. You'll also tell it what channel you want to, so what channels you want to apply the excess uncertainty to. So normally this will be your list of output channels. But you also have to pass it a non-drift corrected channel. So it has to be before you do your drift correction, because when you do your drift correction, you're getting rid of a lot of the variation that you see in your results. So you tell it what channel you want to to work out your excess uncertainty on, and you also tell it the name of your primary reference material. And what that will do is it will calculate that excess uncertainty, and it will record it in the channels for the given selection groups. And now finally, let's talk about calculating associated values, like I mentioned at the start of this presentation. So just to remind you, associated values are those that are results that are associated with one selection, but not necessarily a single channel. So as I mentioned, a correlation between two channels over the duration of a selection would not be a normal result because it's related to two channels, but you could work it out as an associated result. Now, the way you do this in a custom DRS is that you tell iolite how to calculate that associated result for a particular selection. So here's an example where we're telling iolite how to calculate a correlation between two channels. Now, the function that you have to define, so this is defining the function, it has to take a selection as the parameter, because this is the function that will be called for every selection once the DRS finishes. So it takes the selection, and what it does is it returns a result. In the latest version of iolite, it can just return a float, but in general, you can set it up so that it will return a result object. And you do that by importing result from iolite.types. So I haven't put it here, but up above at the start of your script, you would put in from iolite types import result with a capital R. And then the first part of our function, we would create a new result object, and then we try to get our two channels that we're going to calculate a correlation for. In this case here, just as an example, I've tried to calculate the correlation, or I'm calculating a correlation coefficient between the corrected 87-86 ratio and the amount of rubidium expressed as ppm, so the contribution of rubidium 87 and how that relates to this final ratio. So we wrap this in a try just in case we can't get those channels. If that doesn't work, then we'll just return an empty result. Then once we've got those channels, we will get the array of data values within our interval, our selection interval, by calling this data for selection function. So this is the channel, and the channel has a member function called data for selection that takes a selection, and it returns the values in this channel that occur within the bounds of this selection. So we just assign that to an array. We do the same thing with our next channel. So we have two arrays of values here. And then what we can do is we can use this NumPy core coef, which is our correlation coefficient calculation function. And it takes two arrays and it calculates the correlation coefficient for those two. Now it actually returns a matrix that it'll have 2 columns and 2 rows, and we just really want the top right value. So we're just going to say 0 and 1 will be the value. So we're taking our result that we created here and we're setting the value of it to this correlation coefficient that we've calculated here, and then it returns this result. So you must make sure that your function that you define takes a selection and returns a result, whether or not it completes or not. So after we define that function, we then need to tell iolite to run that function after the DRS completes, and we do that by registering an associated result. So we call data.register associated result. We tell it the name of the result that we want to create and the name of the function that will calculate those results. So that's that function we defined in the previous slide. So in our example, we would call data.register associated result. I've called the result the correlation between strontium 87, 86 and rubidium, and I tell it the name of that function to call when it runs. Now, you should define the function outside the run DRS function, but you register it. You run this data.register associated result function within run DRS, so that every time the DRS runs, it makes sure that this registered result is set up and ready to go. If you're looking for an example of this, I suggest checking out the latest version of the strontium isotopes combined rare earth calcium argide and correction DRS, because this has an example in there, this exact example that I've shown here in there. And finally, there are some more advanced, in fact, the sky's the limit really in what you can do in your DRSs. Some of the things that I thought might be interesting as more advanced things, but we're running out of time to discuss, would be something like creating a plot in your DRS settings. So this is again the strontium isotopes combined DRS, and this is showing a correction that you might want to apply. This is just a prototype, so it's not actually real what you might want to do, but it would take some results and would fit a line to them, and you can show the user that plot so they can see what effect that correction is having. I'm not going to show how to do that in this DRS because it would take, so in this presentation, because it would take almost as long as we've already done so far. But check out the strontium isotopes DRS for an example of that. Another more advanced control that you can add is one of these ones that allows you to select multiple reference materials with checkboxes for each one, and that's also in that DRS as well. So if you want to check that out. So let's summarize what we've covered today. We've looked at the two main functions, the settings widget and the run DRS functions that need to be defined in a DRS module. We've looked at the basics of creating new channels, usually based on an existing channel. We've looked at baseline subtraction, because that is something that you'll do in almost all DRSs. We've also looked at interference corrections using both a simple approach and taking into account mass fractionation. We've looked at correcting for mass fractionation in isotope ratios using the Russell equation. Of course, the Russell equation was just an example. You could use any equation that you like, but that's the most commonly used one. We looked at downhole fractionation modeling, so how to calculate the average observed downhole fractionation curve, fitting a line to that, and then applying that correction. And we've also looked at error propagation and how to calculate associated results by both defining them and then registering that function that iolite will use to calculate those associated results. So now, armed with that knowledge, let's talk about your assignment for week 5. For this week's assignment, we want you to write a DRS to process lead isotope data. We've got an example session file that you can use, so you don't have to create an importer. All the data and selections have all been made there, and it's going to be a very heavily truncated DRS that's just going to look at one isotope ratio, because to look at the other ratios would be a matter of copying and pasting. So You don't need to know anything about lead isotope data except that there are 4 isotopes of lead. There are no unchanging ratios, and you're only going to look at one of them, which is lead-208 to lead-206. So your DRS will need a settings widget where the user can set their index channel and their reference material. You can put in a mask as well. That would be helpful. And it's in the template when you click new DRS. The template that's automatically filled in for you has most of those for you, but you will need to add a control so the user can select a reference material to use as the primary reference material. It'll need a baseline subtraction step, so you'll need to subtract the baseline splines from for each mass. Then you'll need to create a lead-208 to lead-206 ratio channel, and this will just be the raw channel, just looking at the baseline subtracted values. Then you'll need to get the true value of that ratio for the selected reference material from the reference material file. Then you'll need to create a channel that calculates the lead fractionation factor, just like we showed in the presentation today. Then you'll need to use the spline of that channel for the reference material to correct for the lead fractionation for all of the 208, 206 lead values. So it's only about 20 lines of code, maybe a little bit more, maybe a little bit less. It's not a lot. There's only a few steps there to do, but it should cover quite a bit of the material that we've covered today, and also quite a lot of the stuff that you would need to write your own DRS. Of course, you can check how well your DRS works by looking at the final 208, 206 values for the secondary reference materials in the example data file. Now, just some tips before you in case you get stuck on them. Just check to make sure that the mask default options are not too stringent. So you might find when you're writing your DRS that you don't see any values at all, and that'll just be because the default mask options are set up for counts per second data, not volts data. So that's something to check. And the other thing is just to check to make sure that the primary reference material that you're using actually has a 208, 206 value in it. And in this case, in the example data, I'd recommend using BCR2G as the primary for your example data. Also, just to save you a little bit of time looking it up, this is the equation that you'll probably want to use when calculating the lead fractionation value. I've put in the atomic masses for 208 and 206 there for you, and you'll need to calculate these ratios here and understand what the rest of this equation is doing. Of course, there are some things in there that are quite tricky, and there's a lot of concepts to cover, but please let us know if you have any questions. We're always happy to help. We hope that these assignments will really help consolidate your knowledge in the material that we're presenting, and that they'll allow you to go off and do amazing work of your own. So please let us know. We're keen to help, and if you have any questions, let us know. Otherwise, happy learning.